Hello, welcome back to Engineering 201. I wanted to pick up where we left off last time, talking about circuit simplification, equivalent resistance, parallel and series elements, and element relationships in terms of if you know the current through something, what's the voltage across it, and things like that. I'd like to use all of that we've talked about in the past to tackle this problem here, and this is going to be kind of a tough problem. One thing you notice right off, it's different from the other problems that we've had in that it has multiple sources. It has 3 sources, and we're going to see that as kind of a indication that maybe we should look at a more advanced method. And so this will be good practice for us in terms of circuit simplification materials from chapters 1, 2, and 3 of your textbook, and hopefully you're still reading those chapters. But it's also going to be motivation as we go into Chapter 4 and node analysis to come up with more robust and advanced methods to analyze things like this. So given this circuit here, what we would like to find is this voltage here, Vs. And when you start one of these things, it's a little bit like putting a puzzle together. You want to start where you have the most information of the puzzle. Oftentimes you start at the edges or the corners and work your way to the middle. Here it looks like we have the most information with this current source. We're told that we have 4 amps going to the right and that the power is minus 24 watts. Let's look at that a little bit then. So we could say if I'll write over here, I'm going to switch pages on you real quick. But if the power is equal to minus 24 watts, we could say that that's equal really to 24 watts supplied. Okay. So if it's supplying power, that means this is going to have to go from negative to positive. So I want to go ahead and put the voltage in, and maybe I will say that this is voltage 1. So I could say then, therefore, that voltage 1 has to be equal to, using Watt's law, of course, power is equal to current times voltage. So voltage is going to be equal to power divided by current. So we have, what, 24, that's our power, divided by our current, which is 4, gives me, what, 6 volts. Okay, so I've got V1 that's 6 volts, and I've taken care of the polarity and the relationships, the negative, by knowing that this is supplied, and putting our voltage then, that this current would have to go from negative to positive to allow it to supply something. Now, I'm going to go through and put a lot of currents on this thing, and I'm just going to do it rather arbitrarily. So let me flip to the next slide here. And we've already established that V1 is equal to 6 volts. We've got that. And let me talk a little bit about how I put these things in. You'll notice V1, that follows with that. I put in I1, and I have just assumed those. And I used a little bit of experience to try and put them in so that I didn't have negative signs in terms of, you'll notice that this current is going opposite that voltage, that this current is going opposite that voltage, so to try and minimize the negative sign. So over here I'm either going to be stuck with a negative sign on both V2 and I2, or hopefully not a negative sign on either one. So I just arbitrarily put in these currents I1 through I6 and really V1 through V6. Just to give us something to talk about so we can label it and call it something rather than saying, well, the voltage across there. So with that, let's continue working here. If I want to figure out what I1 is, I really need to figure out that voltage across there, don't I? So I could say that I1 is going to be equal to, how do I get from here back up to there? Well, I could go this way. Going there is what? Minus V1. And then up here, from there up to there is 12. And then I have to divide that. I'm using Ohm's law. V is equal to IR. So I is equal to V over R. So I better come up with the resistance. What resistance do I have across there? I have 1 and 3 in series. So 3 plus 1 ohms. Okay, and when you put the 6 in here, you end up with minus 6 and 12. That gives you 6 over 4, which is 3/2 of an amp. Okay, so again, I'm trying to find this current I1. I need to find the voltage that's opposite that, so that would be that voltage there. So I could go from here to there and there to there. I mean, this is just like a map. If I'm trying to get from this point to that point, that's where that arrow takes me. An alternate route would be to go this way, which is opposite V1, so I'd have minus V1, and then back up here, which is in the direction of this, so it's positive 12. If you went in this direction, what would that be? It would, of course, be negative 12, wouldn't it? Okay, so I got I1. Well, if I have 4 amps here, and I have I1, which is 3/2, I can figure out what I2 is, can't I? So I could say that I2 is equal to, give me a little bit better pen here. Oh, I was stalling. What'd you come up with for I2? I2 would be equal to this 4 here plus what? I1, right? Well, I1 was 3/2. So we make our substitution for that at 3/2. 4 is what? 8/2. So this turns out to be 11/2 of an amp. Okay. Well, let's see. That's I2, so we could get V2. V2 is really just by Ohm's law. That's going to be equal to I2 times 2 ohms. So that is 11 volts, isn't it? Well, this is kind of fun, like putting a puzzle together. We could talk then about V3. That's the voltage from there up to there. So how can we get there? Well, wouldn't that be the same as from, this is all the same point down here. There's no element in this, so this is all the same point. So going from here to there would be the same as going from there to there, which is V2, and then from there to there, which we already agreed was minus V1. So I could say that I have V2, 11, minus V1, which is 6, which gives me, what, 5 volts? Okay. So again, going from here to there would be the same as going from there up to there, which is V2, and then there to there, which is minus V1. So that's V3. That's opposite of I3, so we can simply say that I3, that's why I try to arrange those opposites so I don't end up with a negative sign between them, because as this current comes down through here, it's going to go from positive to negative, right? So I've got I3 that's going to be equal to, what do we have here? V over R, right? So we would take V3 and we would divide by 2 ohms, which gives me 5/2 of an amp. Well, now that I got I3 and I2, I could talk about I4, couldn't I? I mean, you got I3 coming down here, you got I2 combining with it, so we could say that that's I3 plus I2. Do I have a number for I3? Yeah, that's 5/2. And what's I2? 11/2. Excuse me, what, 16/2 or 8 amps? Okay. Then with I4, I could get, if I've got this, it comes around here, so I could find V4. Do this. I think I've got enough room here. Yeah, say V4 is going to be equal to, it's going like this, the current's going to go like that, so this will be positive and negative, so that's good. So we could just say that it is equal to I4 times what, 2 ohms, which gives me 16 volts. Put this I4 right down in there, 16 volts. Okay, so then we could talk about V5, couldn't we? What's V5 going to be? Well, that's going from this point to this point, isn't it? V5. What's another way to get there? I could say down here, which is V4, crossed here is of course 0 because there's nothing, plus V3, right? which is, what would we get for V4? We get 16, right? It's going to be equal to 16 plus V3, which is 5, which is 21 volts. Now, a lot of times people have a hard time with that equation. That's really just a statement of Kirchhoff's laws. If I was to start here and go around this thing, starting at this point, I could say that I have V5, and then get down to here, I go minus V3 because I've agreed the arrow's up there, so I'm going to have to subtract V3, and then this is 0, and then what do I have up here? Minus V4. That gets me, because this is 0, so V5 minus V3 plus 0 minus V4 gets me back to my starting point. Kirchhoff says that's equal to 0, right? So if I solve for V5, what's V5 equal to? It's equal to V4 plus V3. Is that what we got? It absolutely is. Okay, so this is just a side note here. Kirchhoff's voltage law. That's all I'm talking about when I do this or when I do that. So go back and spend a little time with that. Let's see, I could do I5 then. What's I5? That's that. The voltage is like that, so it's going to go from positive to negative, so it should be positive. I could say that I have V5 divided by 3 ohms, which is 21 over 3, or 7 amps. Now let's see. I've got I4, which is, what did we come up with I4? 8 amps. And I got I5, which we just found was 7 amps. So what's I6 going to be? Well, we could say that I4 plus I5 is equal to I6. What do we have for, so we could say that we have what, I4, which was 8, plus I5, which is 7, is equal to 15 amps. That's what I6 is. Okay, 15 amps. So now that I got 15 amps here, I should be able to talk about V6, because this current is going like this, going to go from positive to negative. So I could say that V6 is going to be equal to what? I6 times 1 ohm. Well, you put your 15 amps in there, and you get 15 volts, don't you? Okay. 15 volts. Well, I can finish then talking about Vs, because the way Vs is oriented, it would be a little bit like an arrow like that, wouldn't it? So let me talk then. You could say, therefore, Vs is equal to what? I'm going from here to there, right? Is there another way to do that? Well, from there to there is minus V6. And then from here to here is minus 12. And then from there to there is minus V5. So I could say that this was minus V6, or minus 15, minus 12, minus V5. Do we have a V5? Yep, 21. What do we come up with there? Minus 48, right? So Vs is minus 48. And that would be volts. And again, this equation here is really just a statement of Kirchhoff's voltage law. That is to say, from there to there would be the same as going from there to there, which is minus V6, because we're going against the arrow. Minus 12, we agreed that this is positive 12, this is minus 12, because you're going from positive to negative, so I have minus 12. And then minus V5, because I'm going against the arrow there. So that's how that worked out. Okay. Well, fairly full page there. When you download the PDF, probably be a little bit easier for you to see, but hopefully this is laid out so that you can get it. What I would encourage you to do is go back to the original problem, put your own variables in there, and see if you can come up with the same answer. This is a great problem to practice your skills from chapters 1, chapters 2, and chapters 3. It's also a good problem as a motivation that coming up with figuring out, well, I go from here to there, that's sometimes hard to do in a high-stress situation like an exam or something. So maybe we can come up with a methodology that will be a little bit more mechanical, and that we do this, and we do this, and we do this. And indeed, our two big methods that we're going to talk about coming up, node analysis and mesh analysis, should deliver that. So without further ado, let's head to node analysis. And I can't overstate this enough. I mean, on this problem, go back to the original problem, take this thing, cover it up with the workup with a piece of paper, and see if you can do it. It's all too easy to sit and look at something like this and go, oh, yep, this makes sense. I can get that. I think when you look at a blank piece of paper with this problem on it, it becomes a lot more difficult. So practice that. Well, let's look at node analysis then. To get into node analysis, and quite frankly, mesh analysis or loop analysis, we'll talk about the subtlety between those names. Students do pretty well at that. We're going to so-called eat our broccoli first here. Node analysis, students struggle with a little more, but the concept is really important, so we want to really figure this out. And node analysis and mesh analysis are huge tools. Certainly in the electrical area, they're big. If you're a civil engineer and wondering why you have to be here, if you look at designing a water system, you have losses in pipes that are similar to resistances. You have pumping stations that are similar to sources. And your analysis is going to look very much like a node or a mesh problem. So coming up with this logical way of thinking extends well beyond these problems. Well, in the past, we've talked about the connection of circuits. Let's say we've got a couple of resistors and we have another resistor there. We've talked about this as a point of connection, or sometimes we talk about it as a node. The node is a connection of two or more elements. Well, with node analysis, we want to talk about an essential node, which is the connection of three or more. So, essential node. So node is just two or more, whereas an essential node is three or more. So something like this, there's a node, whereas something like this is an essential node. If you have two or more elements, you got a node. If you have three or more, you have an essential node. So when we look at node analysis, if n is defined as our number of essential nodes, we will need n minus 1 independent equations to solve. Okay, and it's important that they be independent. If they're not independent, you're going to end up proving 2 is equal to 2 or something like that. So if we have then 3 essential nodes, we will need 2 independent equations to solve that. That's pretty much it for definitions and whatnot. Probably the easiest way to explain this is just to dive right into a problem. So I'll leave this up here. Let's try a problem. Fairly easy problem, hopefully. So we'll say that we have 50 volts here. And 3 amps, 40 ohms, 10 ohms, and 5 ohms. I'm sure I've got that documented correctly. So let's say that we wanted to find the current. We'll just take a variety of currents here. Let's say that we'd like to find, we'll say we're given this. bind. Okay, so given that circuit, I'd like to find the currents through the 10 ohm resistor and through the 40 ohm resistor, so the currents through there. One thing that we have to do with node analysis is we have to take one of the essential nodes. So how many essential nodes do we have here? This is not an essential node. It would be a node, but not an essential node. This, however, is an essential node, and this is the same essential node. You'll notice that there is no resistance in there, there's no element in there, so this point is really the same as that point. If we were to build this in laboratory, this would all be one solder connection. So there's an essential node, and likewise this bottom is really all the same node across here. There's no resistance in either one of these, so this is really all the same, one great big node across the bottom. So I have an essential node there, and I have an essential node there. So it looks like I'm going to have in this problem that n is equal to 2 essential nodes, so I'm going to need one independent equation. So we'll start out nice and easy with this one. Now what we do is we take one of the essential nodes and we make that our reference ground. And then I could talk about this voltage up here. I could say that this voltage was, let's say, V. That would be our node voltage, and when I talk about the voltage at this node, it's always in reference to this. Okay? So it's always in reference to this node down here. So V indicates the voltage here with respect to ground. So then I could put some currents in here. I could talk about, and a lot of times I'll put the currents leaving the node up here. So I'll talk about this as I1. Maybe I'll talk about this as I2, and I could talk about this as I3. Okay, so that's I3. So if I use Kirchhoff's current law, I could say at this node, which is really this whole thing, what do I have going on? I've got I3 that is leaving, plus I1 that's leaving, plus I2 that's leaving, I3, I1, I2, and the only thing that's going in is 3, so I could subtract off 3 or say that that's equal to 3. So what's leaving is what's going in. Now that doesn't really mean that those are leaving. One of these may be a negative number. Maybe I assumed I3 in the wrong direction. Well, that's fine. We'll get a negative number for that, or for I1, whatever the case might be. So we write our node equation. That's our node equation. And then I use my voltage relationships to substitute in there. I mean, right now I have 3 unknowns, I1 and I2 and I3. That's not what I want. So if I talk about I3 in terms of Ohm's law, remember that voltage is equal to current times resistance. So current is equal to voltage over resistance. So let's go talk about this. If this current is going to the left, I'm going to find the voltage that's going opposite that. So this voltage here, what would be that to be the same as? That would be the same as going this way, which is what? Minus 50. Is that right? From there to there is minus 50. And then back up here, from here up to there, by definition, is V. So I could say minus 50 plus V. Minus 50 plus V. Is that right? From there to there would be minus 50 plus V divided by, what's our resistance? 5 ohms. Plus then I1. I1 and I2 are a lot easier because I can really just take the voltage that I have across there, that's V, and divide by, this case it's going to be 10. Here with I2, I know the voltage across there is the same, so I have V, and I'm going to divide by what? 40. And that's equal to 3. So now I have one unknown. That one unknown is the voltage V. So let's see if I can solve that. I could say that I have V over 5 plus V over 10 plus V over 40. is equal to 3. Then let's see, 50 over 5 turns out to be 10. The negative goes away, so I will have plus 10 when I move it to the other side. So I could say that V is equal to 3 plus 10 divided by, what do I have? 1 over 5 plus 1 over 10 plus 1 over 40. So I might be kind of lazy here and grab my calculator, bang that out from there. We could continue to work it with arithmetic if we wanted to. Yeah. So we got 40 volts there. Okay. Now that's kind of neat. That tells me that the voltage at this point with respect to the ground is 40 volts. So if I were to take my voltmeter, put one lead here and one lead there, I should come up with 40 volts across there. Now that's not what I was looking for. I was looking for the current through the 10 ohm and the 40 ohm resistor. So that's really what I'm looking for is I1 and I2. Let's see if we can get that. So I have page 3 here. I'll move to page 4 and see if we can put this in. Okay, so I'm looking for the current through the 10 ohm, so I would like to find the current through the 10 ohm. That's going to be I1. Well, do we have a relationship for I1? Yeah, we said that I1 was really what? V over 10, didn't we? So I1 is equal to V over 10. Do we have a relationship for I2? That's the current through the 40 ohm. Yeah, we got that right there. I2 is going to be equal to V over 40. So this turns out to be 40 over 10, which is 4 amps. Okay. Double check that with my notes. Yeah. And this one turns out to be equal to 40 over 40, which is 1 amp. Again, double check that with my notes. Yep. So we've got 4 amps and we have 1 amp there. I mean, if we wanted to, we could figure out I3. I mean, these are our answers. We've answered the problem here. But if we wanted to look at I3, what would I3 be equal to? Well, it's minus 50 plus V over 5, which is minus 50 plus 40 over 5. So I end up with what? Minus 50 and 40 minus 10, minus 2 amps, don't I? So does that work on our equation? When we go back up and we look at this equation here, if I take I3 plus I1 plus I2, does that equal 3? Well, let's see, what's I3? Minus 2. What's I1? 4. What's I2? 1. Is equal to, say, minus 2 and 4 gives me 2 plus 1. Yep, 3. So that works out. So with node analysis, a lot of times students have a lot of trouble here, and then frankly they have a lot of trouble with algebra. Okay, so this is electrical, and this is algebra. So start on these problems, start with this problem, start with some of the homework problems, see if you can come up with the node equations, and then go through the algebra and try and find the solution. So a great problem to start with, a relatively easy problem. Eventually we'll get into problems where we have multiple equations, we're solving multiple linear equations, we'll get into matrices and whatnot. But this is a good problem to start with, and I encourage you to really dig in on this subject because it will pay big dividends. Well, that wraps up our work today. When we get together next time, we're going to continue on in node analysis and eventually get to mesh analysis. Take care till then, and thanks for watching.